Swayam Prabha. Digital India. Educated India.
Welcome to the NPTEL course on building energy systems and auditing. In the module number 3, we are discussing the building heat load estimation. In that, in the third lecture, we will see the cooling load calculation 1, part 1, and also in the next lecture we will do the part 2. So, in this lecture, we will demonstrate stepwise how to calculate and how to estimate the building cooling load, and if there is a variation of outdoor temperature. If we remember correctly, in the last lecture, the lecture number 11, where we have calculated the cooling load based on a particular outdoor temperature and based on a particular thermal solar radiation. The thermal heat gain through the conductive waves and the radiative waves are calculated for a specific one outdoor temperature and the solar radiation. This process will be the computation process, and the estimation process will be followed by the same flow chart or flow diagram that we were discussed in the last class. So, in that there are 3 steps actually. In the first step, we will calculate the solar air temperature by virtue of the first equation, and the second and the third equation will be giving us the conductive and the radiative heat gain. The radiative heat gain will be applicable for the windows, any transparent surfaces, and for the opaque surfaces, and also for the windows we have to calculate the conductive. This is the conductive one and this is the radiative one, the heat gain. Now, only difference will be what we will discuss in this lecture is in what will be the difference from the lecture number 11 and this lecture number 13 is that this TO, the outdoor temperature, and the I. So, this two, this one the I and this TO, these two will be going to vary. Okay, this is going to be vary for each hour, because as we understand that it is a climatic data and the outdoor temperature is not constant throughout the day. The solar radiation is also not constant throughout the day. The solar radiation is not constant and uniform in the various part of the wall, that means the wall which is in the eastern side, the wall which is in the western side or maybe the southern side will definitely will have the solar radiation not a uniform way or in a particular time. So, we have discussed that one earlier. So, this fluctuation of the solar radiation and the outdoor temperature has to be taken into if we want to calculate or estimate the total heat gain of a building, not for 1 hour, but for the whole day scenario, whole working day scenario. Because a particular building, if it is office building or if it is any kind of the institutional building, it will may work in the daytime, maybe from morning 10 to evening 5 or something like that. So, in that period of time there is a fluctuation in these two environmental parameter, that outdoor temperature and the value of the solar radiation. So, what will be the total heat gain from morning 10 to the evening 5, and what is the peak heat gain? So, from the peak we have to estimate the total amount of the cooling load required, and we have to estimate the what will be the amount of or what is the total capacity of the air conditioning unit or so, and from the beginning, that from the 10 to 5 or whatever this particular period of time. So, we have to see that how much is the total heat gain, and that total heat gain will be equivalent to the cooling load. That much cooling is required for in our tropical country like India. So, that will give a kind of estimation that much amount of energy is required to cool down the particular environment, that is indoor environment. And if now the building is some other type of building, maybe a mall. So, it may work from the morning 10 to the little late night, maybe around 12 in the night or midnight or so, or maybe it is a hospital, then it is throughout the day. So, like that we have to see how what is the total span of the working time, and based on that the outdoor temperature and the solar radiation we need to take. Of course, the solar radiation may be goes to 0 after the sunset or so. So, that part only the outdoor temperature will be calculated, but for the during the daytime both the parameter will come into the picture. So, with a small or simple problem we will start understanding this, and also we will see the some internal load, how to calculate that one. So, suppose I have taken a small building room, or maybe a that I have mentioned as a computer lab, which is in the south, this is the southwest corner of a building, and other two sides are not exposed to the, this north is not exposed to the outdoor, and also the east is also not exposed to the outdoor. Okay. So, these two are not exposed. So, only the heat gain will be possible from the south and the west, and also from the roof. So, I have mentioned that it is a 7 meter by 5 meter room, computer lab with a 4 meter of height. So, the facade area I can easily calculate. The southern facade area is your 7 4s are 28 meters square, whereas the western facade area is 5 4s are 20 meters square. Okay, this is the facade area, and based on the 15% of the WWR, window to wall ratio of both the side, we can actually calculate how much is the total solid wall area, and 15% of this 28 and 20 will be the window area of the southern part and the western part. And this is a ground story or some story that its roof is also going to be open to the atmosphere or open to outside. So, there is a third facade is also there, which is a roof, which is your almost 35 meters square, 7 5s are 35 meters square, roof is also exposed. So, I have to estimate the cooling load for 10 hours, 10 working hours of that particular computer lab, and average some monthly climatic data of some month is given, for month of June suppose is given, like this is the average the data. So, what I have data is given, time series data from morning 9 to evening 6, the temperature, outdoor temperature, it starts from 26 degree and again go as high as maybe 38 degree at 2 o'clock, and then it is again come down. Even we have given the solar radiation in the southern side, the western side and the roof. If you see, the roof is almost exposed to some amount of solar radiation, but southern side has some started radiation, getting radiation from the sun from 11 to almost about 17, that is 5 o'clock, whereas the western side getting radiation from 1 p.m. to the 6 p.m. or so, and the values are given in watt per meter square, and all the material data is also mentioned in the top table. So, U value I have mentioned the SHGC of the window, I have mentioned the surface absorption and the surface conductance. Those two data will be required for your the solar air computation, and indoor set point temperature is kept constant as 24 degrees. So, basically my aim, I have to keep that computer lab at 24 degree centigrade throughout the this 10 hours from 9 to 6, but there is a variation in the outdoor temperature and the solar radiation in the all the three sides, exposed side, and how this changes will going to be happening in the calculation of the load, that cooling load. So, each rows I have to calculate the conductive heat gain, and also, so for each rows I have to actually calculate the this Q equal to A u del T, and also the Q equal to A S H G C into I for each row. For each row I have to calculate, and the del T calculation will be tricky, because every time I will have this T S A minus T n, this del T, and the T S A is going to fluctuate. T S A is going to fluctuate because your I value is fluctuating and the temperature value is fluctuating, and that also fluctuate in the 3 different sides. So, I have to use Excel for computation. Manually it may not be that possible. So, this is the heat gain. So, I have make a table. Of course, this table was cropped from a Excel chart. I will show you the Excel chart. So, the outdoor temperature, and those are the 3 or 4 data which is required to find out the solar air temperature. So, see each time the morning, suppose 9, the outdoor temperature is 26 degree, whereas your I, that is the I value is 0. So, this will be then equal to 0. So, that means this will going to cancel, and this T S A will be equal to T O A, is not it. Similarly, the next hour also it will be 28 degree, will remain 28 degree, because this is 0. Because this is 0 at the 6 o'clock, it is also going to be 28 degree. But from 11 to 17 hours, there is a value, there is a changing value of this I, and based on that there is slight changes or that is noticed in the solar air temperature by virtue of this formula. So, second case what I will do, I have taken this as 50 multiplied by, I am talking about the 11 hour, 11 am. So, it is 50, is not it, and these two are equal, I mean these two are constant. For this is 0.6 is the absorption, and this is 18, and corresponding outdoor temperature is 32 plus. So, this, so that gives me equal to almost 33.66 degrees C. So, like that, by virtue of the Excel computation, I found all the solar air temperature, and then I have the indoor temperature constant, and I can found out the del T. So, here you see I have found out this the conductive heat gain for the southern side. So, this 3 data is now the second layer is required. So, the del T I got by virtue of this minus this. For each rows I know the area, I know the U value, I know SHGC value. So, based on this 4 I can find out the conductive and the radiation heat gain, and I can add up to get the total heat gain. So, that means see the total heat gain in the southern side is also increasing, and its peak it is almost about 1183 watt in about 2 p.m. and then again it is decreasing. So, like that I have to recalculate the same thing for west and the roof, west and the roof. So, this is for the south wall, again I have calculated, I think the calculated for the hourly heat gains also, and then I have calculated for the each part of the facade. So, let me go to the Excel. So, in this Excel, see what is mentioned over here in the table number 1 is the building geometry. So, I have to give the building geometry data, that means what is the length of the north facade, what is the height of the north facade, like that. So, as the north and the east facade is not exposed, So, it is not getting any heat. So, I have put the value 0 0 and WWR is also 0. So, the southern facade is 7 meter as we see and the length, and the west is 5 and the height is 4 and 15% is the WWR, and roof is also 7 and 5 the height. It is not height, but the width and the other part the length 7 5 is the 35. So, and I have here I have to put these green tables are your input tables, and whatever you will get here it is in the other part. So, the U values and the SHGC absorption coefficient and the surface conductance are mentioned over here, and outdoor temperature series data, I north and the I east are 0. So, there is no question of, because it is not exposed. The south and the west things are there, the I values of the roof. So, total kilowatt hour per hour it mentioned over here after calculation. So, in this particular Excel for each the sheet I have calculated, and the final calculation is this, and then I have taken that into the in this particular chart. So, total the kilowatt, how much is the kilowatt calculation is there, and total cooling load kilowatt hour is also mentioned 31.83 by virtue of adding all those. The peak load is 5.98 kilowatt, which is at 2 p.m. So, that means you have to purchase, if you want to purchase any kind of the air conditioner for this room, you have to purchase based on that. So, peak TR is 1.71. So, the by virtue of the divide this 5.9 or 6 divided by 3.5. So, from the south I am getting almost 10.28 kilowatt hours. So, that is nothing but the summation of all the south the heat gain throughout this 10 hours. The west is getting 7.11, roof is highest 14.45. So, that is shown in this bar chart, and the percentage of heat gain from the south, north and the south, the west and the roof are also mentioned. Now, suppose if I have some facade area, suppose I have the eastern facade area also, maybe this is again 5 meter and this is maybe 4 meter same height, and this is also suppose 15% or something, and there are some heat gain because I have to, there are some temperature. So, if I give some morning data, suppose it is 50 and then it is 120 maybe, and then maybe at 11 it is again the 100, and then maybe it is 75 maybe or 75 or something. So, see you have get some value in the there is a bar in the east. So, you will get certainly some values. So, there all the values are going to change, your those values are also going to change. So, suppose you have some you give some better window, I mean maybe you have a 2 layer of the glasses or so. So, it become 3 maybe instead of 5.3 or something. See, things will going to change. If you give some value of the north, maybe it is 7 meter by 4 meter with up to 15% of the WWR, and north may also have some gain maybe 50 and this is maybe 100 and then again 50 maybe in this part. So, you will see the some of the variations or something like that. Okay. So, and your things are changing, changing the kilo. So, what does it mean this kilowatt hour loading 41.07. So, let me go back to PowerPoint presentation. So, PowerPoint presentation shows the earlier one. So, north facade is 0 and I am sorry, the north facade is 0 because it is not exposed, east is also 0, it is not exposed. So, there is no question of any heat gain from the eastern side and the northern side, but there are some heat that will come for this whole 10 hours. This is in kilowatt hour and total heat gain is 31 point. So, I can say that this is the total day demand, this 31.83 kilowatt hour is the total day demand. That means, 31.83 kilowatt hour is the total electricity bill that will come for this particular room for particular day of June, that particular month, for one day only, to run some kind of the air conditioning system or to run some kind of a cooling system, because total cooling load is 31.83, whereas the peak load is 5.98. The peak load, you see the peak load is 5.98 at 12. The peak load is changing, or the load is changing, and the peak load is almost like 6 at 2 o'clock. That means, I have to have a air conditioner which can give me at least 6 kilowatt hour or 1.7 TR capacity air conditioner for this particular room. Why? Otherwise, at 2 o'clock when my load is that particular hour is my load is 5.98 or 6, I will not have that much of cooling effect. Suppose I have purchased only 1 ton, 1 TR or 1.5 TR. So, 1.5 TR or 1 ton will be very well taken care of in these 2 hours or whatever other hours, but at 2 o'clock my demand is 1.7, but my machine is 1.5. So, that will not going to cool that much. That means, your 24 degree set point temperature we cannot be maintained at 2 o'clock or so. So, that will be little bit high, maybe 26 degree, 27 degree, because your total demand is almost 1.7, but your machine can give only output of the machine can give 1.5. Of course, there are a lot of other things also, efficiency of the machine or whatever, but let us assume efficiency is 100%. In that case also 1.5 tonnage of the air conditioning unit will not provide you the best efficient cooling if you put your set point temperature as 24 degree, right. So, we have to purchase accordingly that peak, but if I install 1.7 is not possible. Maybe if I installed 2 tier, it is effectively will be working well. I can get 24 degree temperature at peak time, that is 2 o'clock also, and when it is maybe morning 10 or morning 11, when the load is required less, then it is also can work. The total amount of the air exchange and everything will be less. So, total power consumption for that particular hour will be 1.26 kilowatt hour, next hour it will be 2.61 kilowatt hour, something like that. So, in the that particular day when the temperature, outdoor temperature was given for the month of June and this I values are given. So, for that particular day, in this particular computer lab will actually going to consume 31.83 kilowatt hour. See this, there is a little difference between these two. Peak load I am calculating in kilowatt, not in kilowatt hour, because that is the demand for that particular hour. Now, I am multiplying 10 times 1 hour each, because I have 10 hours of data, 10 hours of working schedule of the particular office or building or computer lab or so. I am adding those for 10 hours and then I am getting almost like 31.83 kilowatt hour is the total energy requirement of this particular computer lab for that given day. Now, for June I have to multiply with 30, because June, or maybe there are some holidays. So, maybe there are 20 working days, so I have to multiply with 20 for those working days or so. So, that will be the total amount of the energy requirement, cooling load required for the month of June, right. So, I may say that this 31.83 multiplied by some 20 days. So, that will be for the June. Similarly, if I know the average temperature and the solar radiation for the month of July, August, September, all the 12 months, I can recalculate this thing for all 12 times and I can find out the what is the demand for the each and every month, and I can calculate the what is the annual demand of total load or so, right. So, based on this way we can actually calculate, but this is a simple calculation for a month, a day of a particular month. So, in fact, I can repeat it for if I have the each and individual day data, I can repeat it 365 days time and I can find out the overall the annual, but it is too much of laborious. So, it is better to have the monthly data. So, 11 or 12 times I have to repeat this particular calculation and I have to add up and then find out the what is the total effect of the annually. So, next one, if I see this particular two graph. So, this is what? This is the graph when I have shown the in the south wall the temperature, outdoor temperature, this is the solar air temperature, this is the solar air temperature for the wall and windows and this is for the roof. So, you see this is the temperature, outdoor temperature is this blue line, window solar air temperature is your this orange line, this is the window which is higher and the wall the temperature, this is wall green. So, that means, if you take the delta T, so if you take the delta T as T temperature outdoor minus temperature in, or if you take delta T as T SA minus T in, there will be a change. There will be a change because there is a fluctuation. So, better if I take this one because that will give me exact kind of the scenario, because solar air temperature is the surface temperature outside of the any envelope surface. Similarly, if you see in the case of the roof, it is also high. I mean, this is high. I mean, if you take some this in your computation, this the data which is shown in the blue line, which is the outside temperature data, your total capacity and everything will be less. Total consumption will show, estimation will be less, but actually it will be high, because it will be actually governed by the solar air temperature. So, next what we will do, we will see some of the internal heat gain. So, because of the people, because of the lights and the illumination features and all, and also depending upon the equipment, there are some kind of a load will be the estimated. So, we can say the equipment loads are the electrical plug loads and the process loads. So, these are the table which from the Koensberger this book I can see this is the some of the body activity of the human being. Based on that, some of the how much watt is the load that can be estimated. So, if you are sleeping, it is almost like 70 watt. If you are somebody is sitting and moderate work like some kind of the computer and some kind of office activity. So, this is 130 to 160 watt. So, that particular data can be taken for any kind of internal heat gain. Similarly, the equipment or the light will radiate some kind of a heat. So, in case of suppose the fluorescent bulb, 90% heat will be released and 10% heat will be actually used for the light. Similarly, the fluorescent is 80%. So, like that, and also for the equipment, what we can do, the equipment will have some kind of its power. Suppose some computer has 100 watt, some machine may have 200 watt, 500 watt, whatever. So, we can estimate the about if the efficiency is epsilon. So, 1 minus epsilon part of the wattage will be actually converted to the heat. We can assume that, because epsilon times W will be actually power consumption to run the machine, excess will be, we will assume that it will be the heat. So, based on this I have recalculated the what will be the internal gain of this particular computer lab. I have estimated that or assumed that there will be 15 computer, there will be 20 CFL lamp or 40 watt which is having a heat output of 60%. There is a computer which is efficiency of 60%. I am sorry, the CFL is heat output is 80%. The computer is having efficiency of 60%. There are 15 computers and there are 15 occupant which will give you 130 watt as a sensible heat. So, just we can directly take that one. There are computers of 200 watt. So, 200 into 1 into 1 minus 0.9 will be the per computer heat output. There are 15 computers, like that CFL is there are 20 numbers and this is the wattage and 0.8 is a the amount of heat that will gain. The occupant is 15 into 130. So, total I can add up, and per hour I can say that almost like 2.9 kilowatt will be the heat gain of this particular, due to this particular internal gain also. And there are 10 hours. So, that means multiplied by 10, 29 kilowatt hour will be the total heat gain for this particular room due to the internal load. So, I have now this is by the old value. So, I can now add up those 29 and 2.9 to get the new peak value and to new the total estimated value for the day. So, the total energy for cooling is just 31 point, this will be for the envelope gain plus 29. So, that is 60.83 kilowatt hour has to be my total heat gain or cooling load required for the whole day based on the envelope gain 31.83 plus 29 is my internal gain. The peak load for the cooling is, which was 5.98 plus 2.9 per hour that we have calculated. So, it will be actually going to be 8.88. So, that means you require 2.5 TR of capacity of. So, what we did, we separately calculated the internal load based on the equipment, based on the number of people will be or number of occupant and the amount of or the number of equipment or so, and we add for each hour, because that will be running for each hour, we can assume that, and then we can actually see the what is the change in the peak load, what is the change in the total load, and based on that we can going to estimate our total cooling capacity, total purchase of the energy, and that is for this particular lecture. So, what we seen is that we have calculated the cooling load based on the variation of the outdoor temperature and the solar radiation, and also we have discussed about the internal loading. Thank you very much.